So we begin our study of waves, and the students say, "Oh, goody, waves, let's go on a field trip." And what they're thinking is that they want to go here. But these are not waves. These are called breakers. They are broken waves. The fact that you can ride on them on a surfboard, the fact that they throw water up onto the sand, the fact that they bang into you, indicate that they are not waves. That if you want to go someplace where there are waves, you have to go out past the breakers to where we have what we call the swells. And these are waves. And if you were to stand in these on your surfboard, or indeed if you were a thrown away bit of litter, what you would find is that you will not, as the wave goes by, you will not be carried forward by the wave. You will be picked up by the wave and then put down again as the wave goes by. Clearly, there is energy in the wave. It gives you gravitational potential energy by lifting you up by a force acting through a distance. But it does not carry you forward. And the fact that it doesn't carry your surfboard or this bottle forward is an indication that the water all around the bottle or surfboard is also only being lifted up and put down as the wave goes by. It is not being carried forward. It's actually more complex than that, but let's keep it simple here at the start. A wave then, transporting energy is going forward with the wave, but the medium is being displaced but not being transported. Here another example of this, that I have a bowling pin, I want to cause it to fall over. One way would be to throw a baseball at the bowling pin, and if I hit it, that would knock it over. That I would be sending energy to the bowling pin, but it would be kinetic energy. It would be matter with motion. That was the nature of the energy that knocks the bowling pin over. I could also make the bowling pin over by putting a wave into a string that I have tied around it, and the wave would advance down the string, and when it got to the end, it would cause the string to move to the side, and it would cause the bowling pin to fall over. But in this case, I am transporting matter to the bowling pin. In this case, I am not. The piece of string right here next to the bowling pin has always been next to the bowling pin. This string back where the wave is right now stays back there. The string does not go to the bowling pin. The string gets displaced, but it is only the energy that goes to the bowling pin. So this one is a wave. This one where you transport matter along with the energy is called a particle. And one of the things that we will kick around later is whether light is a wave or a particle. That is, clearly light transports energy. Does it accompany it with matter or not? That would be the resolution. Turns out it's not a very simple one to resolve. So here is our definition of wave: the transport of energy without the transport of matter. I've also mentioned momentum, that the wave has a directional property as well, a vector quality, that if this bump was put in up, then when it gets to the bowling pin it'll be going up. If you put the bump in down, then when it got to the bowling pin it would still be going down. So there is a directional quality that is also transported by waves. Okay. Very important part of a medium for waves is that it be elastic. When that displacing energy of the wave displaces it, it needs to then have something that returns it to its normal position after the wave has gone on. Otherwise, you cannot have a wave. So that elasticity is very important, that I've got to have somebody holding both ends of the slinky. If there is no tension, no restoring force, then you cannot send a wave. So here is this slinky, and I am sending a wave down it. We say it is propagating in this direction. That's a very rich term. We will talk about it more in class. And I want to know what are 3 different ways we could displace the slinky relative to that direction of propagation. And I ask you to put those on your sheet. Let's see what you can come up with. Now, for a wave, we have a lot of vocabulary that we're working on right now. We have a name for the distance from a crest to a crest. That is indeed called a wavelength. The symbol is a Greek lambda for a wavelength. But it's not just from crest to crest. It's also from trough to trough. It's also from this zero displacement to this zero displacement. It is the distance between 2 adjacent points in the same phase. What about how quickly the wave is jiggling up and down? How many times does it jiggle up and down every second? That's called frequency. The number of waves passing per second, or the number of cycles per second, is its frequency. And we will measure that in hertz, which is the same thing as a cycle per second. The time it takes for a wave to pass a point, let's choose a point, right there. There is a crest at that point now. How long will it be before the next crest is at that point? How long will it be for one complete wave to pass that point? And that's called the period. Use a capital T. Let us consider these 2. If it takes 2 seconds for that crest to get up to this point, that is, for one complete wave to go by, if the period is 2 seconds, how many times does this point go up and down every second? And I think with a little thought you can see that if it takes 2 seconds for that crest to get up here, that it's going to take 2 seconds for it to go up and down. That in 1 second it would go up and down a half a time. A period of 2 seconds, a frequency of a half a second. What if the frequency was 3? What if the frequency was 3? That is, it went up and down 3 times every second. Would that not also mean that this crest here, 1, 2, 3 complete waves would pass that point in 1 second if this was going up and down with a frequency of 3? So how much time would it take for one wave to go by? And the answer is 1/3 of a second. What I'm trying to point out to you is that these 2 are reciprocals of one another. When t is equal to 2, f is equal to 1/2. When f is equal to 3, t is equal to 1/3. Okay, remember that. I want you to recall the definition of average velocity and write it on your worksheet. Stop the show. Write it. You started the show again. This is the stuff from September, that average velocity was the rate of displacing. And so if we want the velocity of a wave, the propagation velocity of a wave, we could see how many seconds it took for it to go 1 meter, or we could see how many meters it went in 1 second. But there's a much more organic, natural distance to ask a wave to go, instead of asking it to go 1 meter. Can you think of a much more organic distance connected with this wave? Ah, yes, it is a wavelength. So I would ask the wave, instead of going forward 1 meter, ask it to go forward 1 wavelength. And how long will it take for this wave to advance by 1 wavelength? Aye, but that's a period. And so it follows from the definition of wavelength and period, and the definition of average velocity, that the velocity of a wave must be equal to its wavelength divided by its period. But we just asserted that the period was the reciprocal, that 1 over period is the same thing as frequency, so it is also from the definitions that the average velocity of a wave is equal to its frequency times its wavelength. And you will apply that truth again and again. Here it is again. So it would seem to be the case that if you doubled the frequency, you would make a wave go twice as fast. Or if you doubled the wavelength, you would make a wave go twice as fast. And that is not the case. Although this equation stands there, it is not a relationship between frequency and wavelength. That in fact, the velocity does not depend upon frequency or wavelength or period, that the velocity of a wave depends solely upon the medium through which it is passing. If it is a non-dispersive medium, we don't need to worry about what that means until later, and it will matter to us later. Right now, let's just ignore that phrase. Velocity of a wave solely dependent upon the medium. I think that's the wrong word. Okay. But, moving on from that factoid, let's deal with this. I've got electromagnetic waves which travel at 3 times 10 to the 8th meters per second through the vacuum of space. Oh, wait a minute, Mr. Houghton. What medium is present in the vacuum of space? You said the velocity was solely dependent upon the medium, but there's no medium in outer space. Yeah, that's kind of problematic, isn't it? It's still the case. Electromagnetic waves travel at 3 times 10 to the 8th meters per second. So a radio wave of 100 megahertz, remember what mega means, would have what wavelength? This is towards the top of the FM dial of radio frequencies. Okay, new topic. Here is a wave, and here is a wave of the same frequency but twice the amplitude. Which one of these two would you say is more energetic? And I hope you would say this one. If this was a spring, I'm shaking the spring much harder here than I was here to make those bigger waves. That this is a matter of elastic energy that you're dealing with here. It is a greater deformation of that elastic medium means more energy. And in fact, the energy goes as the square of the deformation, so too for waves. That the energy of a wave is proportional to the amplitude of the wave squared. Consider this wave, which has the same amplitude as the first one, but twice the frequency. Which one of these two would you say is more energetic? And you think about making these by shaking a slinky. Here I'm going to be much busier, shaking it up and down much more quickly, much faster, much more kinetic energy. And so too for waves, that the energy of a wave is proportional to the frequency squared. That the energy of a wave is proportional to the product, to both the frequency squared and the amplitude squared. If you look in your textbooks, you will see that they have changed this into an equation. They've introduced all kinds of other constants out front. We don't need to deal with it at that level, but I do want you to know this. And apply it. Here you go. Please do these two problems based on this idea. All right, so here is a wave moving across the surface of the water. You see all these arrows. Those are the displacing energies that are what the wave is. The wave moves forward, picking up the water, but after it passes, the water has returned to its previous level. That water does not get transported, but the energy which is displacing it is transported, and it moves across the surface of the water. But here comes another wave, coming closer and closer and closer. Oh no, the two waves are going to hit. But that's okay. This is not like two Volkswagen bugs that are going to collide. It is not matter that is moving towards matter. It is energy that is moving towards energy. And when those two energies reach one another, they will go right through one another, like two flashlight beams. They won't bounce off of each other. But as they pass through, both of their energies will be acting on the water where they superimpose, and so you would take those displacing energies and add them. Here there's no energy from the second wave, and so it is identical, but here you get just a little smidgen from this wave, and it picks it up just a little bit. Here it picks it up a larger amount. Here it picks it up this much, and so on. Over here there's no displacement from the first wave, and so you only have the displacements from the second wave. That the resultant form of the water is something like this, with where they superimpose, they add their displacements to make this new resultant wave. Well, that's what I want you to do in this problem. Here are these two waves coming towards one another, and what would the medium look like at this point in their overlap, in this point in their superposition? And you need to think about those waves as being composed of deforming energies. So here there is no energy from the square wave, and you would add that 0 onto the round wave. And here there is nothing from the round wave, and you would add 0 onto the square wave. And here, where there is non-zeros from both of them, you add their displacements and see what it adds up to, just like I did up here. Which one of these is what the resultant waveform would look like? We're going to do a lot of that. Okay, so here is a wave that is moving across the surface of the deep. What direction is that wave moving? And I hope you can agree that the direction of a wave is going to be normal to the wavefront, which is what we said right here. Good definition. Incident, that means the incoming wave. The wave as it is before something happens to it, before there's an incident. So you will send waves in, and then they will reflect. You'll have the incident wave and then the reflected wave. You'll see more of that. A node, a point in space where superposition, those energies overlapping, continuously causes 0 displacement. So one is displacing the medium up and the other is displacing the medium down, and you superimpose those two and they add up to 0. But it's not a point in time. It's not that they add up in 0 for an instant. And it's not a point on the wave. It's not the 0 displacing point on the wave which propagates forward. This is a point in space, a location, where superposition always causes 0 displacement. The opposite of a node is an antinode, where you get not 0 always, but you get maximum displacement. That's misspelled. Sometimes it will be maximum up, sometimes it will be maximum down, and sometimes it will be 0 at this point in space. but it goes through all possible values, including the maxes. That's what we call an antinode. Superposition, we've already talked about that. And then these, well, we need some pictures for those. So much vocabulary. Reflection, you send a wave up to a barrier or to a change of medium, and energy gets reflected, bounces back. That's reflection. This would be the incident, this would be the reflected. Refraction, which sounds very similar to reflection, get the difference between that R and that L. Refraction is a bending at a change of medium. So, as I said up here, some of this energy would be reflected at that change of medium. I haven't drawn that. What I'm focusing on is refraction. As it enters this new medium, maybe that's going from deep water to shallow water. Maybe it's going from water into pudding, but it's changing medium, and it changes what direction it's going, and that's called refraction. Incident, refracted. Here is interference, this pattern of nodal and antinodal regions caused by superposition, and that superposition is the superposition of two different waves. So I've got two or more. I've got two sources here which are putting out circular waves, but they're interfering. And these gray places here are where the waves from those two sources always cancel. These are points in space where there is always cancellation. That's a nodal line. And then here, in between the nodal lines, is called an antinodal region, and at the center of that antinodal region, there would be an antinodal line, where you would have a point here, which is right now a super low trough, but in a minute it's going to be a super high crest. And between those two times, it's going to pass through a zero. All things passes through the extremes at an antinodal line. Finally, diffraction. I send this wave up to a barrier. The part that doesn't hit the barrier just keeps going, but the part that does interact with the barrier bends, changes its direction, and goes into the shadow, and that is called diffraction. And also present in diffraction are going to be nodal lines. They're going to be harder to see, but they're there. How can that be? That's why we're studying waves.